Good morning, everyone, and welcome to the online energy plan workshop. I hope everybody can hear me okay. My name is David Connolly. I'm calling you from Copenhagen in Denmark, and it's really exciting to have you all here this morning. It's the first time we'll be plan across a global audience, which is nice to go through for the first time. The idea of the workshop today is to present a basic introduction to the energy plan model. So we'll go through a few of the basic functions of the tool, what it looks like, and what hopefully you can use it for in your project or in your company. I have designed the workshop today around your own needs. So the questions that I'll cover today are based on questions that you have sent in and that you would like covered. So to begin, I first of all will just give you a brief overview of the agenda for today. So I'll start with a brief introduction, and then I'll take hopefully 6 or 7 of the key problems that you proposed to me before this workshop. We're not going to take questions during the workshop itself, just because we've experienced some problems with audio sound and also with time, because we're under a bit of time pressure to cover a lot of the questions that were sent in. I can see we ran a poll just when you entered the online meeting about what your experience was with EnergyPLAN, and most of the people today are beginners to the EnergyPLAN tool. So I'm going to start from scratch, I think, today about what EnergyPLAN is for and how it used. Hopefully you can all see my screen and can hear the audio clearly. If you have any problems, please let us know through the chat function, and we have some technical support on hand to hopefully make sure everything runs reasonably smoothly. So to begin, I'll start with my brief introduction, and the first thing I'm going to do is just put up the EnergyPLAN tool, and I'll start with the front page. And I'm going to begin with just a very basic overview of what the EnergyPLAN tool is structured like. Firstly, I should emphasize that EnergyPLAN is not designed to model today's energy system. It's designed to model the energy system of the future. This means that the key components within the EnergyPLAN tool are designed for what the future low-carbon energy system looks like. And this is a very important thing for people to appreciate when they start using EnergyPLAN, because if your objective is to model the next 2 or 3 years and make some analysis about how we should change things in the very short term, then EnergyPLAN is probably not the tool that is most suitable for you. However, if you want to model the very long-term situation of what EnergyPLAN looks like or what an energy system looks like in the next 30 or 40 years, especially if you're looking at a low carbon energy system, then EnergyPLAN is very suitable for you. Because there's a lot of emphasis on modeling future technologies and not a lot of emphasis on modeling today's technologies. So let's start by going through the tab sheets. On the top of EnergyPLAN, there is approximately 5 or 6 different main tab sheets. The input tab sheet is where you put a technical problem with the screen sharing and the microphone. Hopefully I didn't lose you too soon into the presentation. I'll start again by just saying that we're covering the 5 main tab sheets of the EnergyPLAN tool. So I'm covering the components here on top. So the one I was starting with was the input tab sheet, which is the tab sheet that covers most of the technical inputs for the energy system. So this is where you put in things like capacities and efficiencies and so on. The next tab sheet is the cost tab sheet, where you put in any costs relating to the technical components you have on the energy system. And I'll give you some examples of that later on. The third one then is the regulation tab sheet. That's where you decide how does the energy model have to optimize its system. In other words, if you have 2 power plants on your energy system, which one of those power plants should the model choose to use first. These type of decision-making issues is what you decide in the regulation tab. The output tab sheet is where you get the results from an analysis that you run. And finally, the settings are just some basic settings that the tool needs to use in order to function. You can see there's not very many, only energy units and monetary units. So if I just go back to the list of issues that I need to cover today, the first thing that it was requested was that we look into what the optimal amount of wind power or some other form of renewable energy on an energy system. So in order to cover that, I'm going to start by making a very basic example of an energy system in EnergyPLAN and walk you through the steps that we carry out in order to do an analysis. I can see that some of you may be missing a small bit on the left side of the screen, but unfortunately I can't fix it at present because that's what caused the system to crash the last time when we tried to move the left side of the screen. So hopefully you can see enough of it to follow the example. So what I'm going to begin with is I'm going to start by making an electricity system that has a demand and a supply, and we're going to do an analysis where we figure out what is the optimal amount of power plants and wind turbines on that system. So to begin any EnergyPLAN tool, when you open the model, it is always a good idea when you click open to open one of these initialize folder files. The initialize file simply puts all of the inputs in the model to 0, so you start with a blank canvas. The only difference between these two files is that the initialize euro uses euro as the currency and initialize uses Danish kroner. So I'm going to use euro. So when I open this model, you can see now that all of the inputs should be 0. I'm then going to click File and Save As, and I'm going to save this as a new file. Let's call it workshop.txt. So to begin, I'm going to discuss some electricity demand. So I'm just going to say that we have 20 terawatt hours of electricity demand. And in the first analysis, I'm simply going to provide all of this electricity with a power plant. So to go to the power plants, I click the district heating tab and I go to condensing. These are the main power plants in the system, and I'm going to put in 6,000 megawatts of power plants. Over in the fuel distribution on the right hand side, I decide what type of fuel do those power plants use. This is a ratio between the different fuels that the power plants can consume. So in other words, in PP, which is the capacity I've just entered, if I enter in 1 here, for example, then all of the fuel that the power plants use will be natural gas. If I enter another 1 under coal, then 50% of the fuel will be coal and 50% of the fuel will be natural gas. In this example, just to keep things simple, I'm going to use nothing but natural gas. So I'm just going to put a 1 under natural gas, which basically tells the model that 100% of the fuel that the power plants consume should be natural gas. I've now installed, you could say, 6,000 megawatts of power plants using natural gas to meet an electricity demand of 20 terawatt hours over the year. This will be modeled on an hourly basis using the default distribution in place. So for example, the electricity demand will use this default distribution here on the right hand side of the 20 terawatt hours. If you have your own distribution, you can click the change distribution button, and from there you can enter your own hourly profile when modeling whatever system you have at present. But I won't cover that right here because I think there's a lot of descriptions in the user manuals of how to create those distributions and input your own ones. So instead, what I'm going to do is proceed now to the next step. So if I was making this very simple energy system where I have some power plants and a demand, the next thing I would like to do is pay for those power plants and pay for that fuel that I put into the energy system. So I can go to the cost window and fuel, and here I put in the prices that I need to pay for the fuel that I consume. You can see that we only have natural gas, so I only need to put in a price for the natural gas that I consume. The natural gas price today is approximately 10 euros per gigajoule. That's maybe a bit high, but it's approximately that. So I'm just going to use that here as a round number for this example. The other thing I need to pay for are the power plants themselves, and that's done under the investment tab sheet, where you can see a lot of different options for different technologies and what their prices might be. In this example, I'm going to assume that the power plants cost approximately 1 million euro per megawatt. They have a lifetime of 30 years and an operation and maintenance cost of approximately 2% per year. These are figures that we freely provide in a cost database that we maintain, and I can show you at the end of the presentation how to get access to that cost database. Otherwise, you can find cost information like this from organizations such as the International Energy Agency, or quite often national energy agencies keep their own cost files that they use for their own analysis. The final thing you need to put in, as well as the cost of the plants, is the interest rate that you're going to assume. And here I'm just going to apply a 3% interest rate in the top right-hand corner. So now we should have covered everything on the electricity system in this very simple model. We have a demand, we have power plants to supply it, and we're paying for the fuel, and we're paying for the plants themselves. If I want to see the results of an analysis like this, I have two options. These green arrows on these icons show the two different ways I can view results from the EnergyPLAN model. One of them, the result on the left, is where I send the results to an on-screen display. The one on the right is where I send the results to a printout sheet, where I actually print the results to a summary file. And that can be sent to a PDF document, or it can be sent to a physical printout. For this workshop, since we're all sharing information by screen, I'm going to only look at the results with the on-screen preview. So if I click this button, the EnergyPLAN model will run an analysis, and I should get a preview of the results. There's a setting here that's different, like this. So hopefully you can all see this new screen that I'm displaying right now. And this is the on-screen preview of the results. And there's a lot of different numbers, you could say, displayed here when you first see the on-screen preview. The main things that I'm going to point out right now are, first of all, the total fuel consumption you can see is just natural gas. So everything else is zero, because I've said that the only fuel that the power plants will consume is natural gas. So in order to provide my 20 terawatt hours of electricity demand, I consumed 44 terawatt hours of natural gas. The price of operating this simple system is approximately 2 billion euro per year. So that's the price of buying the gas and building the power plants. So you could say this is the starting point for our analysis. We have some very simple figures here, like CO2 emissions, fuel consumption, and total costs that we can use to compare some alternatives to this simple electricity system. So I'm going to use this simple model as the starting point for these issues that I'm going to cover on the list today. The first one, if we go back to the agenda, is to find an optimum level of wind power. So for example, right now I'm only using natural gas on the electricity system. How much wind power should I install as the, let's call it, optimum level? So the first thing I'll just point out is, if we want to build some technical components, we go back to the input tab sheet. The input tab sheet being the tab sheet where you put in technical information. And I go to the renewable energy tab sheet, and here I'll find all my different options for inputting renewable energy. If I go to the wind capacity, I can simply type in an amount, let's say 1000 megawatts. It will use the default wind distribution, which you can change if you have your own local wind distribution file. And that will make an estimated calculation of how much energy you will produce during the year with this amount of wind power. So for example, with 1,000 megawatts and this distribution file, EnergyPLAN estimates that it will produce approximately 2 terawatt hours of wind power electricity over the year, which is approximately 10% of the demand that I originally inputted into the file. If I then go, of course, before I do my analysis, I have to pay for these wind turbines that I install. I go to my cost window. You can now see under the wind, there's 1,000 megawatts added. If I input the costs for this wind power, let's assume it's 1.5 million euro per megawatt, a 25-year lifetime, and a 2% operation and maintenance also. You can see now that I've added some additional costs for this wind power, and if I press the run results, you'll see that the costs, well, the CO2 emissions have reduced, the costs have also reduced. So now the costs of operating that system are lower than 2 billion euro per year. Previously it was just above, now it's reduced to 1,976. So the addition of 1,000 megawatts of wind power has reduced the price of the system, and it has also reduced the CO2 emissions and fuel consumption. So now our gas consumption is 39.8 terawatt hours. So that, of course, just gives you a snapshot of what one wind power capacity can do. But the question here is, what is the optimum level of wind power? So it would take too much time to go and investigate every different capacity that you can install of wind power on the system. So to save you some time, there is a feature in the EnergyPLAN tool that allows you to vary the capacity so you can look at a number of different options. That facility is under the Output tab sheet of the EnergyPLAN tool. Under the Output tab sheet, there's this Run Serial Calculations option. And what this serial calculations does is it allows you to input a variety of different numbers for EnergyPLAN to change one single input and run the results in a series of calculations and give you the results for a variety of different inputs. So for example, if I turn this feature on using this button here on the right, now the series calculator is on, which means that when I press this preview results screen, I'll no longer see the results for just one scenario. I'll now see the results for all of the scenarios in this sheet here. I can pick which input to change by defining the input. So if I click this button here, you can see that the input that I vary is dependent on what I select as the user. So right now the input that I'm going to change is the wind power capacity. So if I start by putting in 0, then 1,000, then 2,000, then 3,000, 4, and so on, what EnergyPLAN will do now is repeat the results for all these different amounts of wind power. And I'll just do it as far as 7,000. I have to then tell EnergyPLAN what result do I want to see for all of these different inputs. So you can click on a variety of different options as the input that you'd like to see the result of. So I'll start by just looking at the total costs. So now what I've instructed EnergyPLAN to do is vary the input of wind power from 0 to 7,000 megawatts in these steps, and for each of those values, tell me what the total cost of my energy system will be. So I'm going to then click the preview results. And then I'll get the results you can see for each of the values. So you can see this is the total annual system cost if I have 0 megawatts. This is if I have 1,000 megawatts of wind, 2,000, 4, 5, 6, and 7, and so on. So then you can, just to expand on this a little bit, this is not a very user-friendly way to view the results. So what we typically do when we use EnergyPLAN is we take an Excel sheet and we copy the results in. So if I call this wind power, for example, and I say that this is 0 megawatts, 1,000, all the way down to 7, then I can go to the EnergyPLAN model, and instead of selecting this run option on the top left, I can select the clipboard option on the bottom left. And now you can see that each calculation is being carried out, and at the end I can simply go to my Excel sheet and I can paste the results in here. So if I then look at these results, we can see that the minimum total annual cost occurs when we have a wind power capacity installed of 4,000 megawatts. And I suppose many people would define cost as the way to identify the optimum level. So you can repeat this process for a number of more, let's say, detailed capacities. So instead of using in steps of 1,000 megawatts, you could start by putting in steps of 100 megawatts, for example, by repeating it with 3,000, 3,100, 3,200, 3,300, all the way up to 4,000 if you wanted to get it down to the more detailed level about what exact wind power capacity provides the lowest annual costs. So if I do it like that again, now I have a much lower resolution down at 100 megawatt level. Then I could also copy the results in once again and get it down at a much more detailed level. I won't go into any more details on that, except to point out that right now, as I mentioned, this was just looking at the optimum from a total cost point of view, but you could also use it from a fuel, from a variety of other different metrics. And these are all listed here. The ones that I'll just highlight are, for example, fuel total. So you could identify what is the fuel consumption for lots of different wind power capacities. So perhaps the optimum wind power is the one that requires the least amount of fuel in the system. And the other one I will highlight is CO2 emissions, for example. That could be another way that you want to identify the optimum level. The next thing then I'll cover, hopefully if you have any other main questions about that, we'll take them at the end just to save some time. The next thing that I'll cover is the electricity storage. Before I begin, I'll just take a 30-second break because I've just lost view of the chat function. So I'll just see if I can get that back in case any of you are sending in any questions. So right now, you could say that I have identified that in this simple system where I'm using gas as the power plant and I'm increasing wind power, that the cheapest wind power penetration occurred at a capacity of about 4,000 megawatts. So what we can investigate, for example, in this simple energy system is what happens when we add some electricity storage to this simple model. Can we increase the amount of wind power that we use on the system? So let's go back to EnergyPLAN, and I'm going to start installing some electricity storage. I'm going to turn off my series calculator for now, and I'm going to take a clipboard. I'm going to put in 4,000 megawatt, which was the cheapest option from my series calculations. And then I'm going to take a snapshot of these preview results. So when I click the preview results that I mentioned earlier, where I get an overview of all the results, I want to take a picture of all of these results and put them into the Microsoft Excel workbook as a snapshot of what we're looking at. So let's go to the out. I'll turn off the later, and then I'll select clipboard. I'll go to my Excel sheet. I'll call this gas and wind. And then I'll paste in a copy of the results that I have for that particular scenario. So now you can see all of the results that we presented under the preview results panel are now copied in to the Microsoft Excel sheet. And that was using the output and clipboard function as long as the series calculator was turned off. So we'll move on now to installing some electricity storage. So if I go to my input tab sheet once again, and as I mentioned a few times now, this is where I put in technologies, for example. I go to the electricity storage tab, and then I have two primary options. The first option is where I can put in some form of hydrogen storage. The second option is where I can put in some form of electricity storage. In the electricity storage inputs, there's no, you could say, specific requirements as to what exact technology this is, because the inputs that EnergyPLAN requires are generic enough to represent any major electricity storage technology. So for example, what EnergyPLAN asks for is using the terminology of pumped hydroelectric energy storage. And pumped hydroelectric energy storage is the most common type of electricity storage, and that's why the terminology is, let's say, described in that way. But in reality, you can use these inputs to represent any other type of electricity storage also by just defining capacities and efficiencies. So what you're asked for in this and these inputs are three main things, I suppose. The first key thing you need is a charging capacity or a pump capacity. So this is the amount of electricity that the energy storage facility can consume in order to charge. So if I put in, for example, 1,000 megawatts here, then it means I can send 1,000 megawatts of extra wind power to the electricity storage device at any time. If I also put in a 1,000 megawatt turbine capacity, it means I can take out 1,000 megawatts of electricity from the electricity storage device at any time. This is a very typical situation where you would have the same amount of charging and discharging capacities. Then in the storage capacity, I can put in something like 2 or 3 gigawatt hours would be very typical for something in this scale range. So now what I've told EnergyPLAN is that I have an electricity storage device that has a charging capacity of 1,000 megawatts, discharging capacity of 1,000 megawatts, and a storage capacity of 2 gigawatt hours. There's also these efficiencies here that represent how effective the electricity storage is at charging and discharging. You could say that this efficiency is where you can distinguish between different types of electricity storage devices. For example, a pumped hydroelectric plant typically have charging and discharging efficiencies of around 90%. But then you might have a battery, for example, that you want to model, and that might have lower efficiencies, let's say 70% and 70%, if that's what the technology you're modeling is capable of. So in other words, by using these capacities and efficiencies, you can represent a variety of different electricity storage technologies. One is I've added an electricity storage to the system. So now I have gas power plants, I have wind turbines, and I have some electricity storage. So if I go to my Excel sheet, I'm going to make a new scenario here called gas and wind and electricity storage. So I'm going to take the results from EnergyPLAN by going to the output tab sheet. The series calculator is turned off, so when I click clipboard, then I'll get all of the results onto my clipboard. I go to my Excel sheet and I press paste. And then all of the results from this scenario where I had electricity storage, wind and gas power plants will be added into the Excel sheet. Now that I have both the results from the electricity storage with and without, I can compare the two different situations with one another. So for example, if I look at the gas and wind and electricity storage scenario, I can see that I had a CO2 emission of 5.5 million tons, whereas if I look at the gas and wind scenario, I had a CO2 emission of also 5.598. So the electricity storage in this situation only reduced the CO2 emissions by 5.59 to 5.55. So it had a relatively small effect on improving the amount of wind power I could integrate in this particular scenario. It is then possible, like we did before, instead of just using 4,000 megawatts of wind power like I have right now, perhaps I can increase the amount of wind power, and that will use the electricity storage more effectively. So once again, what I can do is I can go to the output tab sheet. I can turn on my series calculator and I can run the results like I did previously with a variety of different wind power capacities. Just for the sake of this example, once again, I'll measure the total costs of the system by clicking the clipboard. And you can see the model is then going through all of these 8 different scenarios, calculating the total costs. If I then go back to the Excel sheet, my original one, and I'll call this the electricity storage scenario, I can paste in my costs, and you can see that overall the costs were reduced slightly compared to the original scenario. So now, for example, the 4,000 megawatt scenario has a slightly lower cost with the electricity storage installed. However, for those of you who have been keeping a close eye on what I've been up to, I haven't actually paid for any of this electricity storage yet. So I have at the moment free electricity storage. So I need to actually pay for installing these electricity storage capacities. To do that, I go to my cost window. I go to the electricity storage section where you can see pump and turbine. So these are the charging, discharging, and storage capacities. And here I can add in some costs for the electricity storage device that I just built. I'm not going to go through all of those steps just to save some time and move on to the next topic. But you can see that the process here we would repeat is the same as we did for the gas and wind power technologies earlier with the costs. Then I just also point out in the note for this workshop that my own PhD actually focused on electricity storage and how it can be modeled in EnergyPLAN. So if anyone is interested in looking more into depth at electricity storage, then I would highly recommend that you download my own PhD to have a look at how we went about developing that feature. The next thing I'll cover is flexible demands in EnergyPLAN. Flexible demands are a way to model, I suppose, the smart grid or flexible electricity demands that we expect to see in the future. So in order to model flexible demand, the first thing I will do is delete the electricity storage just to avoid complicating the results that we see. So I'm just going to remove that electricity storage capacity from my simulation. And to model flexible electricity demand, I go to the electricity demand tab sheet. And at the moment, the only electric demand that I've inserted is 20 terawatt hours of what I would call conventional electricity demand. This is typical electricity consumption that we have today, where whenever there's an electricity demand, we have to meet it whenever it occurs. So for example, I might want to transfer 10% of that electricity demand from being non-responsive to being responsive. In other words, making it demand side manageable. If I want to do that, I see reduce, let's say I remove 2 terawatt hours from the conventional type of electricity demand, so I take away 2, then I can move 2 down to what we call flexible electricity demand. Is this working now? Hopefully you can see the screen a bit clearer now. So if we go here and we add in 2 terawatt hours to this flexible demand over 1 week, what I'm now telling is that 10% of my electricity demand can be shifted over a 1 week time frame. So EnergyPLAN takes each week at a time. It looks at what is the weekly demand that represents, and it checks if the system can benefit from moving electricity demand around over a 1 week period. So in other words, it divides this 2 terawatt hours into 52 equal weeks, and then it checks to see if it can move that demand over a weekly period in order to improve the amount of wind power that it's integrating. If I put this 2 terawatt hours in the 1 day situation, then it would divide the 2 terawatt hours into 366 equal days and check how much it can move electricity demand within a 1 day time period. So in other words, I would have a shorter length of time that I can move electricity around in order to benefit the overall system. And once again, it's the same feature for the 4 weeks input. For example, then, if I have a 1 week time span in which I can move electricity around, the next thing that I have to tell EnergyPLAN is what's the maximum amount during any given hour that I'm allowed to move by. So the max effect represents what's the maximum amount of electricity during 1 single hour that can be moved. So you could say that the 2 terawatt hours represents a volume of electricity that can be moved over the full period, and the maximum effect represents the maximum amount that can be moved within any given hour. So if, for example, I keep these settings of 18 terawatt hours and a 2 terawatt hour flexible demand, I can run some new scenarios with additional wind power to see, does it help my system to be able to move electricity around in this way. So let's try it out and see if having 2 terawatt hours of flexible electricity demand will improve the way wind power is integrated onto my system. So if I go to the output window, I have the series calculation on, and I have the amount of wind power varying from 0 to 7,000 megawatts once again. I then press clipboard. It's now running the analysis once again, but this time instead of electricity storage, I now have some smart grid technology or flexible demand over a 1 week period. So I will call this the smart grid scenario, and I'll put in the costs, and now you can see that in comparison to our original scenario, the price has reduced because I'm now using more wind power and replacing even more natural gas because I can move electricity around and integrate some of this wind power. As before with the electricity storage, many of you will be wondering how I can conclude that because I haven't paid for this smart grid feature. And what you'll find when you go to the cost window in EnergyPLAN is that there's no input here under the investment costs to pay for all of this smart grid technology. So if you want to model a scenario like this that doesn't have an inbuilt cost function related to it in the EnergyPLAN model, then you have to add in a customized cost manually. And you do that by going to the cost and additional window. And in the additional window, there's these customizable inputs for adding costs that are not accounted for. So what I can type in here, for example, is installing smart grid meters. So I can say that these smart grid meters have a lifetime of 20 years, an operation and maintenance of 2%, and then I can type in here what was the total price of installing all of the smart meters necessary in order to create this 2 terawatt hour flexible demand over a 1 week period. So this allows you then to add in costs of components that EnergyPLAN cannot automatically consider. I'm going to leave it there for now as well, because I think if you are interested in that topic, hopefully you have enough to get you started on doing some basic analysis, and I'll move on now to the next topic. So I'll delete these inputs for the smart grid or flexible demand scenario, and I'll go back to my original 20 terawatt hours of normal conventional demand. The next question then we'll cover is the hydropower that is in the system. So there's 3 different types, and we were asked what are those different types and what do they represent. The input tab has the technical characteristics. So once again, I go to input. Hydropower is a renewable energy, so I'll go to the renewable energy tab, and here you get a sample of 2 of the different types of hydropower: river hydro and hydropower. And what these represent are 2 different types of ways that the hydro plants can operate. River hydro is similar to wind power in the sense that you have no control over when electricity is produced from the river hydro plant. So in other words, if I type in 1000 megawatts of river hydro, I put in an hourly distribution. This one is incorrect, but let's just imagine there was an hourly distribution of hydropower production. Then EnergyPLAN would calculate based on this hourly production and this capacity, how much electricity do I get, and EnergyPLAN would have to use this electricity whenever it is produced. In other words, the model would have no control over dispatching the power at different times. In comparison, if I said that this 1000 megawatts was actually conventional hydropower, then I can install hydropower that also has some storage capacity behind a dam. So in other words, if I say that there's 1000 megawatts of conventional hydropower and there's also some water stored behind a dam that I can turn on and off, then EnergyPLAN, instead of just using the electricity whenever it's produced, can actually use the storage behind the dam to utilize this hydropower in a more beneficial way for the energy system. The way then that this is modeled is that you input what the energy flowing into the hydro reservoir is. So if, for example, I say that there's 5 terawatt hours of water flowing into this hydro reservoir, then based on this capacity, EnergyPLAN will estimate what is the electricity production that we can get over the year, but this will not be an exact replication of what the electricity production will look like, because during the analysis, EnergyPLAN might use this storage capacity to increase or decrease the amount of production from the conventional hydro power plant. So just to then recap, river hydro occurs when we can only use the electricity as it's generated. Conventional hydro occurs when we can control the output of the hydro power plant. In addition to that, some hydro power plants actually install pumps so that they can pump some of the water back into the upper reservoir of the dam once they have consumed it. So you can also add in a pumping capacity if you want to be able to send energy back into the reservoir after it has been consumed. But this is not pumped hydroelectric energy storage. This is a hydropower dam facility that has the ability to pump back. Then the third type of hydropower is the typical pumped hydroelectric energy storage site where you have a pump, a turbine, and a storage capacity like we covered earlier. So in this situation, there's no inflow of water like you have in a hydropower plant. This is an isolated water reservoirs with upper and lower facilities. So they're the three types of hydropower. River hydro, where you can't control the production. Hydropower, where you can adjust the production due to the addition of a dam, which can store water. And then pumped hydroelectric energy storage, which has no water inflow and is simply an electricity storage device with an upper and lower reservoir. So I hope that covers the three main ways that you can model hydropower in EnergyPLAN. The issue is about the condensing power plants. I think I'll give you a break here from looking at the details of the EnergyPLAN window and just start by giving you a small story about what EnergyPLAN is designed for once again. As I mentioned at the beginning of this presentation, which is maybe a long time ago now since we had been cut out during that process, is the whole purpose of why EnergyPLAN exists and what it's used for. And as I mentioned during that discussion, EnergyPLAN is not designed to model today's energy system, but instead it is designed to model the future energy system. Because it is designed to model the future energy system, power plants are not modeled in a lot of detail in EnergyPLAN. This is because when we run our scenarios for the future of the energy system, we have a lot of wind power and solar power on our electricity grid. Because we have all of this wind and solar power, the amount of hours in which power plants are operating are reduced dramatically. So, for example, today power plants may produce 80 to 90% of the electricity on our grid, but in our future scenarios, power plants can produce as little as 10% of the electricity on the electricity grid. So it's just important to recognize that the role that power plants has to play in the future is much different to the role that it has to play today. And for that reason, power plants are modeled under the input and district heating tab as only two different types of capacities, what we call PP1 and PP2. So if I just go back to the screen again, if we have the input and district heating tab, at the very bottom we have two different ways or two different capacities that we can input for power plants. PP1 is the main type of power plant production. When I refer to power plants, I should also clarify that I'm referring to electricity only generation. I'm not referring to combined heat and power where you produce electricity and heat together. This is electricity only production. And for electricity only production, we have PP1 and PP2. Each of those power plants has a capacity, a total capacity, an efficiency, and a fuel distribution. So for PP, it's PP1 over here is the fuel distribution. For PP2, over here is the fuel distribution. When I want to model power plants, I put in the capacity and I put in the type of fuels like we did earlier for natural gas. The only reason that PP2 exists in addition to PP1 is to be able to model power plants that are very different to the average plant. In other words, almost always we include most of the power plants in PP1. So we include, let's say, coal power plants, combined cycle gas turbines, biomass power plants, and things like that. The typical way that we use PP2 is if we have some really inefficient peaking power plants that are not used very often during the year, but they might have an unusual fuel distribution, a very low efficiency, and a very high operating cost. So a typical way that we would use PP2 is if we have something like 300 megawatts of peaking plant it might have a very low efficiency because it only comes on for a few hours, something like 20%, and it might consume something like oil. So right now I've inputted a capacity, a low efficiency, and an unusual fuel that it consumes. So this is just an example of a way that I would distinguish between PP1 and PP2. When EnergyPLAN runs an analysis, it will always use PP1 first if it is more efficient. When it has run out of PP1 capacity, it will then move to PP2 capacity. So it will prioritize what is the most efficient type of condensing power plant to use. Another way that EnergyPLAN can be told to operate is to use the cheapest type of power plant. So you could also use PP2 to model a very extreme cost in a power plant. For example, if you had a very cheap or a very expensive power plant, you could model it as PP2, and then EnergyPLAN would use whichever one is the cheapest. And that depends on what way you tell EnergyPLAN to operate. And as I mentioned during my introduction, the way that we construct EnergyPLAN to operate occurs under the regulation window. And under the regulation window, we have two different types of optimization strategies: technical optimization and market economization. If I select market economic optimization, it will choose the cheapest type of power plant to operate. If I click technical optimization, it will pick the most efficient type of power plant to operate. So this depends on the instructions, you could say, that you give EnergyPLAN as an input. Then just finalize, we are currently investigating the possibility of adding additional PPs, but this is something that we haven't prioritized too much because power plants play such a small role in the future energy system. But it is something that could happen if we get the resources to code in additional PPs so that people can model power plants in a more distinct way, for example, by separating each fuel rather than combining the fuels with one another. So hopefully then that gives you an explanation of what PP1 is and what PP, the options for power plant capacity in the future. I think we're running tight on time, so I'm not going to cover the last topic about power to gas. So maybe that's something that we can cover in a future workshop if people would like to attend that one. I'll end by just handing over the mic to anybody who wants to ask some questions. But just before I do that, just one thing that some of you may be interested in from joining today is what the future EnergyPLAN looks like. So I'm just going to give you a very sneak preview as to what we're currently working on in the development team to improve EnergyPLAN as a model. So for those of you who are familiar with EnergyPLAN, you can see that we're currently working a lot on changing the interface compared to what it once looked like. So earlier today I was showing you these small buttons on the top for running the analysis, but now these buttons are much bigger, and we're also working on changing the tab sheet layout so that it's a bit more intuitive where you need to go to find your technologies. So we're working very hard at the moment on improving the graphical user interface to make it even more user friendly. And that's a sneak peek of what's to come down the line. I'll stop sharing my screen just for a minute now to see if I can get the chat back. And if anyone wants to ask any questions, please feel free to send us some comments. I'll leave it there. And thanks very much yourselves for attending. It was great to have everyone here. Thank you for your time. And please let us know if you would like to attend one again, because we'll run this in the future if there's a demand for it. Enjoy the rest of your day, and we'll hopefully talk to you again sometime.